Hi guys, so thank you for joining me. I'm going to talk about how to use basically machine vision and deep learning for running on your mobile device and producing basically autonomous and helping us to produce autonomous driving. Right. So at Nexar, our goal is to basically get rid of car collisions. And specifically, we want to eliminate car collisions as much as we can and fatalities. The interesting phenomena that has been happening in the last few years is that the interest in autonomous vehicles have increased exponentially in the last few years. And of course, the premise of having an autonomous vehicle is that the autonomous vehicle uses a computer to control the vehicle, and that's why you're getting a safe driving experience. In reality, what happens is that also the number of fatal crashes, the number of fatalities that you have, those hard collisions in the US has also increased exponentially since 2014. And this is attributed basically to the fact that the economy is better, so people are driving more, and the fact that you get much more distractions, so you have many more apps on your phone, you have better infotainment systems. And of course, that's not something we really want to have. So one of the key technologies for reducing car collisions is called a vehicle-to-vehicle communication network. And this technology is supposed to reduce accidents by 70 to 80%. That was the premise. It's a decade-old technology. And the idea is that you equipped each vehicle with a radio transmitter, and this radio transmitter basically sends the state of the vehicle, what the vehicle does, to the other vehicles. And by joining this network, vehicles can understand what other vehicles are doing. And of course, if there is a potential for a dangerous situation, the driver can get an alert and avoid that dangerous situation. Unfortunately, this technology has not caught on yet. And I think the key reason is the fact that how do you bootstrap such a network? And so if you think about it, when you have a small number of users in the network, when you have only a small number of those V2V enabled vehicles, the value of the network to the other users is small. And this also gives a low incentive for car manufacturers to basically deploy this technology within vehicles. So the key question is, what can you do now? How can you help with car collisions now instead of waiting 5 to 10 years till we have autonomous vehicles on the road? And the way that we look at it at Nexar is that we want to use commodity hardware and to deploy such a network. And the most common, the most prevalent hardware is your smartphone. So the idea is that we want to turn your smartphone into a dashcam app. So basically, you run an app on your phone, you put your phone in front of your windshield, and the phone basically records whatever's happening on the road. And the other mode of operation is that you pair your phone with an existing dashcam, and the number of dashcams is increasing exponentially in the last recent years. And then you get a sensing device that basically that sees what happens on the road. And this sensing device, your phone, has both compute and built-in connectivity, so you can build the V2V network that you want. So what are the benefits that you're getting from such a V2V network as a driver? So the first benefit that you're getting is, of course, that the system records whatever happens and automatically uploads the data to the cloud. So if, unfortunately, something bad happens and you're involved in a collision, you can easily grab the evidence from the cloud. The other thing that it does is that the system can actually give you active warnings. It can tell you, hey, there's a dangerous situation, please react to it. And so people can avoid those dangerous situations. And this whole area of helping drivers and of helping drivers to drive better is called driver assistant systems. And that's kind of the focus of what we're going to talk about. So we're going to talk about how to build the technology that provides drivers with driving warnings. So a little bit about our approach in general. So we have what we call the sensing device, which is your phone. And that phone basically can, so the phone has inertial sensors. So it has an accelerometer and a gyro. And using those, you can actually figure out how a person is driving, if he's doing a hard brake or if he's steering the wheel. The other thing that you have in the phone is a very important sensor. You have a camera. And that allows the phone to figure out what's happening or to understand the road and figure out the interaction with other vehicles. And the way that you do that is you couple this sensing ability with a deep learning network, with a machine vision model that takes the data that you have on the phone and gathers the insight. So it can get like a raw image and figure out, hey, these are the vehicles, these are pedestrians in this image. And when you take all these census devices and put them in one big network, you're getting basically a network effect. So now you can generate warnings that are for scenarios where things are happening outside of your line of sight. So, for example, somebody that's driving into intersection and his line of sight is blocked due to another vehicle, and there's a pedestrian walking, and he or she can't see that pedestrian. And on the other hand, there's another sensor, there's another Nexar vehicle that can actually see that pedestrian. And in this case, that other vehicle can send a message and basically alert the driver, and the driver can react to that pedestrian that he can't see. So that's the big premise of having a V2V network. All right. What I'm going to talk about in this talk is basically share with you some of the insights we learned of how do you build deep nets, how do you build deep learning networks that can run efficiently on your mobile and provide all these driver assistant warnings. So we call our approach, our network, MUNET, which stands for Multitask Unified Network. And we're going to explain why is it multitask unified and why are those things are important. So to put things in context, driver assist data, it's all about corner cases. I think you can see here some interesting corner case. But the idea is that if you actually want to build a warning system, it's not enough to capture 90%, or it's not enough to get to 90% accuracy. You actually want to get to 95% accuracy. Sorry, you actually want to get to 99% accuracy. And the way to do that is to continuously basically capture the rare events, those dangerous scenarios, and automatically update your system to recognize them and improve and constantly improve. So how do we do that specifically? So we have our phone. The phone runs some sensor fusion algorithm that basically allows it to detect a potential dangerous scenario. And then we take and then once we have such an event, we take the data that corresponds to that event, so all the kinematics data, all the location data, the video data that we have, and pass it through a set of deep nets. And in particular, if, for example, we see a rare case that we haven't seen before, we run it through human annotators that go and annotate and specifically label that particular use case, and we add it to our database and retrain the models. Once we do that, we have an improved model. We take the model and adapt it to the particular environment where we want to run it. So, for example, taxis in New York look different from taxis in San Francisco and taxis in Tel Aviv. And once we do that, we deploy it back to the device. So there is basically a continuous feedback loop that goes basically that you take data from the phone, collect, improve your models, and feed that back to the phone. And just to give you a few statistics, so we have been operating for more than a year. Up till now, we collected more than 10 million corner cases of driving. So that can be accidents, near accidents, obstacles on the road, etc. We annotated around 10 million images to be able to build these models. And the other aspect that is really important for us to build a robust system, it's also important to collect those corner cases under a diverse set of environments. So you want to capture corner cases that happen during the daytime. You want to capture those that happen during the night or dawn time. You want to be able to capture scenarios under different weather conditions, rain, snow, etc. And of course, across different geographies and of course around different countries. And if you feed all that information to the model becomes more and more robust. So in our case, we have data from more than 80 countries that we use to train our models. Okay, so when you actually want to take this, when you want to take these models and run them on the phone to generate safety warnings, there are multiple challenges that you need to address. So one key challenge is that you actually need to have an efficient deep learning network architecture. Because the phone has limited compute power and limited memory, you have to have an architecture that takes that into account. So you cannot just take off-the-shelf algorithms and run them. And luckily, the research community has been working really hard in the last year, 2 years, to take existing models which are really big and have have large time complexity, and trying to reduce them as much as possible. And there's a bunch of work like SqueezeDet, YOLO, and others. That the key thing that they do is they try to reduce the network as much as possible, while not significantly hurting the performance of the network. So that's kind of, they want to reduce the capacity of the network till a certain point where where performance is still okay. But all of these attempts in the research community are actually focused on a single task. So basically, yeah, you can build one network for detecting vehicles, one network for detecting pedestrians, but unfortunately, due to the limitation that you have on your mobile device, you cannot run multiple parallel networks. So you need somehow a way to merge all these networks and build a common architecture that can run multiple tasks on a single in a single network. So and also, it's not only that you need to do multiple tasks. So it's not only that you need to detect different types of objects. You also need to detect some attributes that are really relevant for the road scene. Not general attributes, but things that are relevant to the road scene. For example, you want to know if the vehicle in front of you is relevant. Sorry, you want to know if the vehicle detected is in front of you or not. So you'll know if there is a potential, if there is any possibility of a collision or not. Maybe that's just a vehicle that's parked on the side. And the other thing you actually need to do is object tracking. So the question is, how do we combine all of those things, basically doing multitasks, object tracking, and attribute recognition in one network? And that's what I'm going to talk about. And before that, let me talk a little bit about what does ADAS, or Advanced Driver Assistance System, really means. So the way we look at it is we look at it at 3 levels. The most basic level for ADAS or for driver assist systems is level 1, which I think most of you already know. It's a warning. There's the forward collision warning, which basically tells you that that warns you when you're too close to the vehicle in front of you. There is a lane departure warning that means that alerts you when you're drifting from your lane. That's the most basic one. The more advanced features that actually you can find them in high-end vehicles are pedestrian warning or cyclist warning. So these give you warnings when you're too close to a pedestrian, etc. And there's the level 3, what we call level 3, and we think that this is super interesting because with this technology, we can actually get into more complex scenarios. So for example, you can give someone a warning when he's crossing a red light. So if you can detect traffic lights, you can generate red light warnings. Or you can get lane level assist warnings. So when somebody is navigating and is not on the right lane, you can provide a warning, and so the driver will return to the right lane. Okay.
Watch out. Vehicle stopped ahead of you.
Okay. So, cool. So in this particular talk, to make things more concrete, I'm going to talk about two use cases. So I'm going to talk about the forward collision warning, which is the one that you see on the left, and the traffic light alert, which you see on the right, and basically describe how do we build a network that can support these two features. Okay. Okay, so let's talk a little bit about the challenges that we have when we're building a forward collision warning. So the first challenge that we have is basically we want to be able, given an image, we want to be able to detect all the vehicles in that image. So ideally what we want to do is put bounding boxes like we see here around the vehicle. And we want to classify the type of the vehicle. So is it a car, bus, truck, or a pickup truck? The other thing that we want to do is we want to figure out what's the relative lane position of the detected vehicle. And this is important because I want to figure out, am I on a potential collision course with this vehicle, or it's something that is not relevant to me at all. And the typical approach to do that is basically the kind of the common approach that people use is to take the image and segment it and basically figure out where the road is and segment it into the different lanes. And that is, while this is something that you can do on regular machines, it will be pretty costly to do that on a mobile device. So the trick that the trick you can actually do is to add a simple attribute to each object that you detect. So for each object that you detect, you can say, hey, is this object on my lane or not on my lane? And by doing that, you can actually get lane-level localization, which is sufficient for generating those warnings, so sufficient for generating the forward collision warning, and still gives you efficient perception. So how does such a network look like? So the basic network has, on the left side, you can see it has the input image, and then we have a bunch of convolutional layers. And these convolution layers, at the end of the day, generate a feature map. Basically, the network, what we do here is that, given an image, the network is smart enough to encode this image or encode what we see in the world into a set of features. Then what we want to do, given this vector or given this set of features, we want to do in a single pass, in a single shot, we want to be able to do three things. One, to run a detection, then to classify. So we want to detect the vehicle, we want to be able to classify the type of a vehicle and figure out if it's on my relative lane and figure out the relevant lane of that vehicle. And this is typically done by putting different branches or different heads at the output of this backbone or the backbone of the network. So, and the reason we want to do it in a single shot is because we want to be efficient. We don't want to do multiple passes. So let me show you how does this thing look like on when we run it, this network, when we run it either on an Android phone, or this is an Android phone or iOS phone at 50. It's running. The latency here is 50 milliseconds, so you can do it 20 frames per second. So let's see what's the quality that the network can get, and just I'll explain the colors that we have here. The red bounding box means that this is a vehicle on my lane, whereas the other colors of the bounding box indicate that these are vehicles on different lanes. All right. Now let's talk about the traffic light. So let's assume we started with a simple network which can detect vehicles, and now we want to add traffic light capabilities on top of that. So of course we need to be able to detect traffic lights and figure out what their color or state is. But there are two unique things for correctly detecting traffic lights. So the first one is the fact that traffic lights can be extremely small. So suddenly we need our network, Okay. Suddenly we need our network to support both small objects and big objects. And the other one is that we need to understand the full road context, because if, for example, we look here, we see that we have two green traffic lights, and those are relevant to you only if you're going straight, and one red traffic light, which is relevant only if you're going left. So you have to have this global context to really understand the relevancy of the traffic light. So basically, to iterate on a little bit on the challenges and how you solve them. So when you want to combine these two tasks, the traffic light detection and the forward collision warning, you have to look at different dimensions. So one is efficiency. So basically, you want to have a shared backbone. You want to share computation resources across multiple tasks. You want to be able to support multi-scale objects. You want to be able to support vehicles that are really close to the camera and traffic lights that are really far away. And you want to be able to put these attributes or labels that say, is this information relevant to me or not? So how does it look like? So we take the network we had before, and now on top of that, we add the traffic light. We add the traffic light inference. So as before, we have the shared backbone, which is the feature maps. And the interesting thing about CNNs or convolutional networks is that there is an interesting trade-off between localization and generalization. So as you move forward in the layers of the network, you're getting much better generalization, but your localization, your ability to detect the objects at good resolution, deteriorates. So since we want to be able to detect traffic lights at really small resolution, we actually put the detection of the traffic lights somewhere in the middle of the network. But for the determining if that traffic light is relevant or not, that functionality we actually put at the end of the network where we have really good generalization, when we need to have that global context. So detection is done somewhere in the middle of the network when we can get good localization, and the relevancy is done at the end of the network. And that's a nice trick that you can do to basically provide these features. And of course, you need to build a mechanism that allows you to train from all of these data sets. So you need to be able to train with vehicles, traffic lights, pedestrians, etc. So let me show you what can be done on your phone today. So this is kind of running the full MUNET network, full deep learning network on my ride to work. So we're putting bounding boxes on vehicles. So the red one means that the red bounding box means that it's on my lane. As we capture the traffic lights, we analyze their state and show that on the left corner. And you can also see that we're doing one more function that we didn't talk about it here, which we're figuring out the driver's own self-lane, and that's shown in the right-hand corner. And all of this can be done with your existing phone, iPhone 7 and more, iPhone 7 and higher. Model size is not big, it's like around 6 megs. And all of this takes 50 milliseconds to do. So you can do it at 20 frames per second. All right, so just before I summarize, I want to talk a little bit about where Nexar is and where we're headed. So Nexar launched the V2V network a little bit more than a year ago in New York. And then we spread to other cities in the US and other locations. We actually got to a few thousand drivers in New York. And the interesting thing is that even with few thousand drivers, well, 6,000, it's not few, so with thousands of drivers, there's some intersections where we actually can see, where we visit. We have a Nexar driver visiting every 2 minutes. And the interesting thing to look at is the network, the V2V network effect. So this graph shows that there is an exponential effect, and I'll explain. The y-axis shows the number of meetups. So the number of occurrences where vehicles are close to one another and thus basically can share relevant information with one another. And the x-axis shows the size of the networks, how many miles are driven. And what you can see here is exponential growth. So if I add one more driver to the network, it actually increases the potential meetups, the potential occurrences to send warnings by an exponential number. So that shows the impact of the network. And this is how we look at the network. So this is one of our monitoring tools, and it shows you the different vehicles in New York. So each dot is a vehicle located on the map. And on the right-hand side, you can see what are these vehicles, what things these vehicles are viewing. So this is, of course, this is a capture of a live view from a few months ago. And before I summarize, the two things that I want you to take away from this talk is, first, that you actually have to build, if you want to run perception algorithms, if you want to run machine visions at the edge, you have to use a special architecture that really supports multiple tasks in an efficient way. And this can be actually done on your phone, as we demonstrated. And the other thing is that once you have that, you can build your network and grow your network. So hopefully all of us will have a much safer driving experience. That's it. Thank you.
Any questions?
So the question is, what type of data do we collect, and what's the business model, I think? Yeah. So the data that we collect is basically the videos or the images of dangerous or potentially dangerous situations on the road, all these corner cases, as well as all the sensory data, the kinematics data. So we have a huge database of all of that, which we use to train our. Yeah, this is all gathered from the smartphone or from the dashcam. And then the business model for now, we're talking with insurance companies to use our network basically to. The key thing for them is actually providing. So they would like to provide, or they like the idea of providing insurance discounts to drivers that use such a system, because of the warnings and because we can capture evidence in case of a collision and do automatic reconstruction. And in the longer term, it's about selling data. So we have huge amounts of data, and we plan on monetizing that. Yeah, sure. So the question was, here we show, all the warnings we show here are based on line of sight, whereas I mentioned that the V2V network can give you larger effects beyond the line of sight. And the question is where we're standing with respect to that. So the answer I can give you, stay tuned. We'll announce a few really interesting, cool things this year. Yeah. Yeah, so the question of the esteemed gentleman is, are there any privacy issues? Of course, there's tons of privacy issues, and the way that we look at it is, our policy is that the data belongs to the driver, so we don't look at the data. The only thing we can do is we summarize the data and help us to train the models, but initially the data owner is the driver itself. So that's how we address that.
Last question, please.
Yeah. All right, so the question is, if we're uploading raw data, continuously raw data to the cloud, how does that affect battery usage and bandwidth use, etc.? So we're not doing that. Basically what we have a really smart system that uploads only when needed. So we basically, during a normal ride, we don't upload anything. So only when the driver gets home and connects to the Wi-Fi, we upload a little bit of that ride, not everything. But when we do sense something dangerous is happening, like the person hitting the hard brakes or something dangerous from the vision, then we upload like a video of 40 seconds, but only for that particular incident. So we're very strict on uploading only the interesting or dangerous events, and the rest we upload at really low resolution. So that's how we deal with that. So it really depends on the algorithm let's take it offline, but there's like a dynamic policy that decides what you do when.
Thank you.
Thank you, guys.